The standby reservoir is connected to the System B reservoir for pressurization and servicing. The positive pressure in the reservoir ensures a positive flow of fluid to the pumps. The reservoirs have a standpipe that prevents the loss of all hydraulic fluid if a leak develops in the engine-driven pump or its related lines. The engine-driven pump draws fluid through a standpipe in the reservoir, and the AC motor pump draws fluid from the bottom of the reservoir. Figure 12, 63. End of page 12 to 38. Pumps. Refer to Figure 12, 64. For the following description. Both A and B hydraulic systems have an engine-driven pump, EDP, and an ACMP. The System A engine-driven pump is installed on the number 1 engine, and the System B engine-driven pump is installed on the number 2 engine. The AC pumps are controlled by a switch on the flight deck. The hydraulic case drain fluid that lubricates and cools the pumps return to the reservoir through a heat exchanger. Figure 12, 65. The heat exchanger for the A system is installed in the main fuel tank number 1, and the heat exchanger for the B system is installed in the main fuel tank number 2. Minimum fuel for ground operation of electric motor-driven pumps is 1,675 pounds in the related main tank. Pressure switches, located in the EDP and ACMP pump output lines, send signals to illuminate the related low-pressure light if pump output pressure is low. The related system pressure transmitter sends the combined pressure of the EDP and ACMP to the related hydraulic system pressure indicator. Filter units. Filter modules are installed in the pressure, case drain, and return lines to clean the hydraulic fluid. Filters have a differential pressure indicator that pops out when the filter is dirty and needs to be replaced. Power Transfer Unit, PTU. The purpose of the PTU is to supply the additional volume of hydraulic fluid needed to operate the autoslats and leading edge flaps and slats at the normal rate when System B EDP malfunctions. The PTU unit consists of a hydraulic motor and hydraulic pump that are connected through a shaft. The PTU uses System A pressure to drive a hydraulic motor. End of page 12 to 39. The hydraulic motor of the PTU unit is connected through a shaft with a hydraulic pump that can draw fluid from the System B reservoir. The PTU can only transfer power and cannot transfer fluid. The PTU operates automatically when all of the following conditions are met. 1. System B EDP pressure drops below limits. 2. Aircraft airborne. 3. Flaps are less than 15 degrees but not up. End of page 12 to 40. Landing Gear Transfer Unit. The purpose of the landing gear transfer unit is to supply the volume of hydraulic fluid needed to raise the landing gear at the normal rate when System A EDP is lost. The System B EDP supplies the volume of hydraulic fluid needed to operate the landing gear transfer unit when all of the following conditions are met. 1. Aircraft airborne. 2. Number 1 engine RPM drops below a limit value. 3. Landing gear lever is up. For either or both main landing gear not up and locked. Standby hydraulic system. The standby hydraulic system is provided as a backup if System A and or B pressure is lost. The standby system can be activated manually or automatically and uses a single electric ACMP to power. 1. Thrust reversers. 2. Rudder. 3. Leading edge flaps and slats, extend only. 4. Standby yaw damper. Indications. A master caution light illuminates if an overheat or low pressure is detected in the hydraulic system. An overheat light on the flight deck illuminates if an overheat is detected in either System A or B, and a low pressure light illuminates if a low pressure is detected in System A and B. Boeing 777 hydraulic system. The Boeing 777 is equipped with 3 hydraulic systems. The left, center, and right systems deliver hydraulic fluid at a rated pressure of 3000 psi, 207 bar, to operate flight controls, flap systems, actuators, landing gear, and brakes. Primary hydraulic power for the left and right systems is provided by 2 EDPs and supplemented by 2 on-demand ACMPs. Primary hydraulic power for the center system is provided by 2 electric motor pumps, ACMP, and supplemented by 2 on-demand air turbine-driven pumps. The center system provides hydraulic power for the engine thrust reversers, primary flight controls, landing gear, and flaps/slats. End of page 12 to 41. Under emergency conditions, hydraulic power is generated by the ram air turbine, RAT, which is deployed automatically and drives a variable displacement inline pump. The RAT pump provides flow to the center system flight controls. Figure 12.66, left and right system description. The left and right hydraulic systems are functionally the same. The left hydraulic system supplies pressurized hydraulic fluid to operate the left thrust reverser and the flight control systems. The right hydraulic system supplies pressurized hydraulic fluid to operate the right thrust reverser, flight control systems, and the normal brake system. Figure 12.67. End of page 12 to 42. Reservoir. The hydraulic system reservoirs of the left and right system contain the hydraulic fluid supply for the hydraulic pumps. The reservoir is pressurized by bleed air through a reservoir pressurization module. The EDP draws fluid through a standpipe. The ACMP draws fluid from the bottom of the reservoir. If the fluid level in the reservoir gets below the standpipe, the EDP cannot draw any fluid any longer, and the ACMP is the only source of hydraulic power. The reservoir can be serviced through a center servicing point in the fuselage of the aircraft. The reservoir has a sample valve for contamination testing purposes, a temperature transmitter for temperature indication on the flight deck, a pressure transducer for reservoir pressure, and a drain valve for reservoir draining. Pumps. The EDPs are the primary pumps for the left and right hydraulic systems. The EDPs get reservoir fluid through the EDP supply shutoff valves. The EDPs operates whenever the engines operate. A solenoid valve in each EDP controls the pressurization and depressurization of the pump. The pumps are variable displacement inline piston pumps consisting of a first-stage impeller pump and a second-stage piston pump. The impeller pump delivers fluid under pressure to the piston pump. The ACMPs are the demand pumps for the left and right hydraulic systems. The ACMPs normally operate only when there is high hydraulic system demand. Filter module. Pressure and case drain filter modules clean the pressure flows and the case drain flows of the hydraulic pumps. A return filter module cleans the return flow of hydraulic fluid from the user systems. The module can be bypassed if the filter clogs, and a visible indicator pops to indicate a clogged filter. The heat exchanger, which is installed in the wing fuel tanks, cools the hydraulic fluid from ACMP and EDP case drain lines before the fluid goes back to the reservoir. Indication. The hydraulic system sensors send pressure, temperature, and quantity signals to the flight deck. A reservoir quantity transmitter and temperature transducer are installed on each of the reservoirs, and a hydraulic reservoir pressure switch is located on the pneumatic line between the reservoir pressurization module and the reservoir. End of page 12 to 43. The ACMP and EDP filter modules each have a pressure transducer to measure pump output pressure. A temperature transducer is installed in the case drain line of each filter module and measures pump case drain fluid temperature. A system pressure transducer measures hydraulic system pressure. A pressure relief valve on the EDP filter module protects the system against overpressurization. Figure 12.67. Center hydraulic system. The center hydraulic system supplies pressurized hydraulic fluid to operate these systems. Figure 12.68. 1. Nose landing gear actuation. 2. Nose landing gear steering. 3. Alternate brakes. 4. Main landing gear actuation. 5. Main landing gear steering. 6. Trailing edge flaps. 7. Leading edge slat. 8. Flight controls. Reservoir. The hydraulic system reservoir of the center system contains the hydraulic fluid supply for the hydraulic pumps. The reservoir is pressurized by bleed air through a reservoir pressurization module. The reservoir supplies fluid to the ADPs, the RAT, and one of the ACMPs through a standpipe. The other ACMP gets fluid from the bottom of the reservoir. The reservoir also supplies hydraulic fluid to the landing gear alternate extension system. The ACMPs are the primary pumps in the center hydraulic system and are normally turned on. The ADPs are the demand pumps in the center system. They normally operate only when the center system needs more hydraulic flow capacity. The RAT system supplies an emergency source of hydraulic power to the center hydraulic system flight controls. A reservoir quantity transmitter and temperature transducer are installed on the reservoir. A hydraulic reservoir pressure switch is installed on the pneumatic line between the reservoir and the reservoir pressurization module. Filter. Filter modules clean the pressure and case drain output of the hydraulic pumps. A return filter module cleans the return flow of hydraulic fluid from the user systems. The module can be bypassed. End of page 12 to 44. The heat exchanger cools the hydraulic fluid from the ACMP case drains before the fluid goes back to the reservoir. ADP case drain fluid does not go through the heat exchangers. The ACMP and ADP filter modules each have a pressure transducer to measure pump output pressure. A temperature transducer in each filter module measures the pump case drain temperature. A system pressure transducer measures hydraulic system pressure. Pressure relief valves in each ADP filter module prevent system overpressurization. A pressure relief valve near ACMP C1 supplies overpressure protection for the center hydraulic isolation system, CHIS. Center hydraulic isolation system, CHIS. The CHIS supplies engine burst protection and a reserve brakes and steering function. CHIS operation is fully automatic. Relays control the electric motors in the reserve and nose gear isolation valves. When the CHIS system is operational, it prevents hydraulic operation of the leading edge slats. ACMP C1 gets hydraulic fluid from the bottom of the center system reservoir. All other hydraulic pumps in the center system get fluid through a standpipe in the reservoir. This gives ACMP C1 a 1.2 gallon, 4.5 liter reserve supply of hydraulic fluid. The reserve and nose gear isolation valves are normally open. Both valves close if the quantity in the center system reservoir is low, less than 0.40, and the airspeed is more than 60 knots for more than 1 second. When CHIS is active, this divides the center hydraulic system into different parts. The NLG actuation and steering and the leading edge slat hydraulic lines are isolated from center system pressure. The output of ACMP C1 goes only to the alternate brake system. The output of the other center hydraulic system pumps goes to the trailing edge flaps, the MLG actuation and steering, and the flight controls. If there is a leak in the NLG actuation and steering or the slat lines, there is no further loss of hydraulic fluid. The alternate brakes, the trailing edge flaps, the MLG actuation and steering, and the PFCS continue to operate normally. If there is a leak in the trailing edge flaps, the MLG actuation and steering, or the flight control lines, the reservoir loses fluid down to the standpipe level, 0.00 indication. This causes a loss of these systems, but the alternate brake system continues to get hydraulic power from ACMP C1. If there is a leak in the lines between ACMP C1 and the alternate brake system, all center hydraulic system fluid is lost. End of page 12 to 45. Nose gear isolation valve. The nose gear isolation valve opens for any of these conditions. 1. Airspeed is less than 60 knots. 2. Pump pressures for ACMP C2, ADP C1, ADP C2, and the RAT is less than 1,200 psi for 30 seconds. 3. Left and right engine RPM is above idle, left and right EDP pressure is more than 2,400 psi, and the NLG is not up, the NLG doors are not closed, or the landing gear lever is not up for 30 seconds. The first condition permits the flight crew to operate the NLG steering when airspeed is less than 60 knots, decreased rudder control authority during taxi. The second condition permits operation of the NLG actuation and steering if the hydraulic leak is in the part of the center hydraulic system isolated by the reserve isolation valve. The third condition permits operation of the NLG actuation and steering if there has not been an engine burst and the other hydraulic systems are pressurized. The nose gear isolation valve opens when pressure is necessary at the NLG. If the NLG is not fully retracted or the NLG doors are not closed, the nose gear isolation valve opens to let the NLG complete the retraction. When the landing gear lever is moved to the down position, the nose gear isolation valve opens to let the NLG extend with center system pressure. Central hydraulic system reset. Both valves open again automatically when the center system quantity is more than 0.70 and airspeed is less than 60 knots for 5 seconds. Both valves also reset when the center system quantity is more than 0.70 and both engines and both engine-driven pumps operate normally for 30 seconds. Figure 12, 69. Aircraft pneumatic systems. Some aircraft manufacturers have equipped their aircraft with a high-pressure pneumatic system, 3000 psi, in the past. The last aircraft to utilize this type of system was the Fokker F-27. Such systems operate a great deal like hydraulic systems, except they employ air instead of a liquid for transmitting power. Pneumatic systems are sometimes used for. End of page 12 to 46. 1. Brakes. 2. Opening and closing doors. 3. Driving hydraulic pumps, alternators, starters, water injection pumps, etc. 4. Operating emergency devices. Both pneumatic and hydraulic systems are similar units and use confined fluids. The word confined means trapped or completely enclosed. The word fluid implies such liquids as water, oil, or anything that flows. Since both liquids and gases flow, they are considered as fluids. However, there is a great deal of difference in the characteristics of the two. Liquids are practically incompressible. A quart of water still occupies about a quart of space regardless of how hard it is compressed. But gases are highly compressible. A quart of air can be compressed into a thimbleful of space. In spite of this difference, gases and liquids are both fluids and can be confined and made to transmit power. The type of unit used to provide pressurized air for pneumatic systems is determined by the system's air pressure requirements. High-pressure systems. For high-pressure systems, air is usually stored in metal bottles at pressures ranging from 1000 to 3000 psi, depending on the particular system. Figure 12, 70. This type of air bottle has two valves, one of which is a charging valve. A ground-operated compressor can be connected to this valve to add air to the bottle. The other valve is a control valve. It acts as a shut-off valve, keeping air trapped inside the bottle until the system is operated. Although the high-pressure storage cylinder is light in weight, it has a definite disadvantage. Since the system cannot be recharged during flight, operation is limited by the small supply of bottled air. Such an arrangement cannot be used for the continuous operation of a system. Instead, the supply of bottled air is reserved for emergency operation of such systems as the landing gear or brakes. The usefulness of this type of system is increased, however, if other air pressurizing units are added to the aircraft. Figure 12, 71. Pneumatic system components. Pneumatic systems are often compared to hydraulic systems, but such comparisons can only hold true in general terms. Pneumatic systems do not utilize reservoirs, hand pumps, accumulators, regulators, or engine-driven or electrically driven power pumps for building normal pressure. But similarities do exist in some components. End of page 12 to 47. Air compressors. On some aircraft, permanently installed air compressors have been added to recharge air bottles whenever pressure is used for operating a unit. Several types of compressors are used for this purpose. Some have 2 stages of compression, while others have 3, depending on the maximum desired operating pressure. Relief valves. Relief valves are used in pneumatic systems to prevent damage. They act as pressure limiting units and prevent excessive pressures from bursting lines and blowing out seals. Control valves. Control valves are also a necessary part of a typical pneumatic system. Figure 12.72 illustrates how a valve is used to control emergency air brakes. The control valve consists of a 3-port housing, 2 poppet valves, and a control lever with 2 lobes. In Figure 12.72a, the control valve is shown in the off position. A spring holds the left poppet closed so that compressed air entering the pressure port cannot flow to the brakes. In Figure 12.72b, the control valve has been placed in the on position. One lobe of the lever holds the left poppet open, and a spring closes the right poppet. Compressed air now flows around the open left poppet, through a drilled passage, and into a chamber below the right poppet. Since the right poppet is closed, the high-pressure air flows out of the brake port and into the brake line to apply the brakes. To release the brakes, the control valve is returned to the off position. Figure 12.72a. The left poppet now closes, stopping the flow of high-pressure air to the brakes. At the same time, the right poppet is opened, allowing compressed air in the brake line to exhaust through the vent port and into the atmosphere. Check valves. Check valves are used in both hydraulic and pneumatic systems. Figure 12.73 illustrates a flap-type pneumatic check valve. Air enters the left port of the check valve, compresses a light spring, forcing the check valve open and allowing air to flow out of the right port. But if air enters from the right, air pressure closes the valve, preventing a flow of air out of the left port. Thus, a pneumatic check valve is a one-direction flow control valve. End of page 12 to 48. Restrictors. Restrictors are a type of control valve used in pneumatic systems. Figure 12.74 illustrates an orifice-type restrictor with a large inlet port and a small outlet port. The small outlet port reduces the rate of airflow and the speed of operation of an actuating unit. Variable restrictor. Another type of speed-regulating unit is the variable restrictor. Figure 12.75. It contains an adjustable needle valve, which has threads around the top and a point on the lower end. Depending on the direction turned, the needle valve moves the sharp point either into or out of a small opening to decrease or increase the size of the opening. Since air entering the inlet port must pass through this opening before reaching the outlet port, this adjustment also determines the rate of airflow through the restrictor. Filters. Pneumatic systems are protected against dirt by means of various types of filters. A micronic filter consists of a housing with 2 ports, a replaceable cartridge, and a relief valve. Normally, air enters the inlet, circulates around the cellulose cartridge, and flows to the center of the cartridge and out the outlet port. If the cartridge becomes clogged with dirt, pressure forces the relief valve open and allows unfiltered air to flow out the outlet port. A screen-type filter is similar to the micron filter but contains a permanent wire screen instead of a replaceable cartridge. In the screen filter, a handle extends through the top of the housing and can be used to clean the screen by rotating it against metal scrapers. Desiccant/moisture separator. The moisture separator in a pneumatic system is always located downstream of the compressor. Its purpose is to remove any moisture caused by the compressor. A complete moisture separator consists of a reservoir, a pressure switch, a dump valve, and a check valve. It may also include a regulator and a relief valve. The dump valve is energized and de-energized by the pressure switch. When de-energized, it completely purges the separator reservoir and lines up to the compressor. The check valve protects the system against pressure loss during the dumping cycle and prevents reverse flow through the separator. Chemical dryer. Chemical dryers are incorporated at various locations in a pneumatic system. Their purpose is to absorb any moisture that may collect in the lines and other parts of the system. Each dryer contains a cartridge that should be blue in color. If otherwise noted, the cartridge is to be considered contaminated with moisture and should be replaced. Emergency backup systems. Many aircraft use a high-pressure pneumatic backup source of power to extend the landing gear or actuate the brakes if the main hydraulic braking system fails. End of page 12 to 49. The nitrogen is not directly used to actuate the landing gear actuators or brake units, but, instead, it applies the pressurized nitrogen to move hydraulic fluid to the actuator. This process is called hydraulics. The following paragraph discusses the components and operation of an emergency pneumatic landing gear extension system used on a business jet. Figure 12(76). Nitrogen bottles. Nitrogen used for emergency landing gear extension is stored in two bottles, one bottle located on each side of the nose wheel well. Nitrogen from the bottles is released by actuation of an outlet valve. Once depleted, the bottles must be recharged by maintenance personnel. Fully serviced pressure is approximately 3,100 psi at 70 degrees Fahrenheit per 21 degrees Celsius, enough for only one extension of the landing gear. Gear emergency extension cable and handle. The outlet valve is connected to a cable and handle assembly. The handle is located on the side of the co-pilot's console and is labeled MR-LDG gear. Pulling the handle fully upward opens the outlet valve, releasing compressed nitrogen into the landing gear extension system. Pushing the handle fully downward closes the outlet valve and allows any nitrogen present in the emergency landing gear extension system to be vented overboard. The venting process takes approximately 30 seconds. Dump valve. As compressed nitrogen is released to the landing gear selector/dump valve during emergency extension, the hydraulic pressure actuates the dump valve portion of the landing gear selector/dump valve to isolate the landing gear system from the remainder of hydraulic system. When activated, a blue dump legend is illuminated on the LDG-GR dump V-switch, located on the flight deck overhead panel. A dump valve reset switch is used to reset the dump valve after the system has been used and serviced. Emergency extension sequence. 1. Landing gear handle is placed in the down position. 2. Red light in the landing gear control handle is illuminated. 3. MR-LDG gear handle is pulled fully outward. 4. Compressed nitrogen is released to the landing gear selector/dump valve. End of page 12 to 50. 5. Hydraulic pressure actuates the dump valve portion of the landing gear selector/dump valve. 6. Blue dump legend is illuminated on the LDG-GR dump switch. 7. Landing gear system is isolated from the remainder of hydraulic system. 8. Hydraulic pressure is routed to the open side of the landing gear door actuators, the unlock side of the landing gear uplock actuators, and the extend side of the main landing gear side brace actuators and nose landing gear extend/retract actuator. 9. Landing gear doors open. 10. Uplock actuators unlock. 11. Landing gear extends down and locks. 12. 3 green down and locked lights on the landing gear control panel are illuminated. 13. Landing gear doors remain open. Medium pressure systems. A medium pressure pneumatic system, 50 to 150 psi, usually does not include an air bottle. Instead, it generally draws air from the compressor section of a turbine engine. This process is often called bleed air and is used to provide pneumatic power for engine starts, engine de-icing, wing de-icing, and in some cases, it provides hydraulic power to the aircraft systems if the hydraulic system is equipped with an air-driven hydraulic pump. Engine bleed air is also used to pressurize the reservoirs of the hydraulic system. Bleed air systems are discussed in more detail in the Power Plant Handbook. Low-pressure systems. Many aircraft equipped with reciprocating engines obtain a supply of low-pressure air from vane-type pumps. These pumps are driven by electric motors or by the aircraft engine. Figure 12(77) shows a schematic view of one of these pumps, which consists of a housing with 2 ports, a drive shaft, and 2 vanes. The drive shaft and the vanes contain slots, so the vanes can slide back and forth through the drive shaft. The shaft is eccentrically mounted in the housing, causing the vanes to form 4 different sizes of chambers, A, B, C, and D. In the position shown, B is the largest chamber and is connected to the supply port, as depicted in Figure 12.77. Outside air can enter chamber B of the pump. When the pump begins to operate, the drive shaft rotates and changes positions of the vanes and sizes of the chambers. Vane number 1 then moves to the right, separating chamber B from the supply port. Chamber B now contains trapped air. As the shaft continues to turn, chamber B moves downward and becomes increasingly smaller, gradually compressing its air. Near the bottom of the pump, chamber B connects to the pressure port and sends compressed air into the pressure line. Then chamber B moves upward again, becoming increasingly larger in area. At the supply port, it receives another supply of air. There are 4 such chambers in this pump and each goes through the same cycle of operation. Thus, the pump delivers to the pneumatic system a continuous supply of compressed air from 1 to 10 psi. Low-pressure systems are used for wing de-icing boot systems. Pneumatic power system maintenance. Maintenance of the pneumatic power system consists of servicing, troubleshooting, removal, and installation of components, and operational testing. The air compressor's lubricating oil level should be checked daily in accordance with the applicable manufacturer's instructions. The oil level is indicated by means of a sight gauge or dipstick. When refilling the compressor oil tank, the oil, type specified in the applicable instructions manual, is added until the specified level. After the oil is added, ensure that the filler plug is torqued and safety wire is properly installed. The pneumatic system should be purged periodically to remove the contamination, moisture, or oil from the components and lines. Purging the system is accomplished by pressurizing it and removing the plumbing from various components throughout the system. Removal of the pressurized lines causes a high rate of airflow through the system, causing foreign matter to be exhausted from the system. If an excessive amount of foreign matter, particularly oil, is exhausted from any one system, the lines and components should be removed and cleaned or replaced. End of page 12 to 51. Upon completion of pneumatic system purging and after reconnecting all the system components, the system air bottles should be drained to exhaust any moisture or impurities that may have accumulated there. After draining the air bottles, service the system with nitrogen or clean, dry compressed air. The system should then be given a thorough operational check and an inspection for leaks and security. End of page 12 to 52. End of chapter 12. Chapter 13 is next.